For centuries, we humans have looked up at the night sky and wondered about our place in the cosmos. One such enigma is dark energy. Imagine a force so powerful it dictates the fate of the universe. Galaxies are racing away from each other at an accelerating rate. This implies a mysterious force counteracting gravity's pull. Dark energy constitutes 68% of the universe's energy density. The year was 1998. Two teams of astronomers were measuring the universe's expansion rate. They expected gravity to slow the expansion. Instead, they found the expansion was speeding up. This discovery shocked the scientific community. We now call this force dark energy. Here's the real kicker. Dark energy makes up about 68% of the universe's total energy density. The stars we see, the planets we know, even the mysterious dark matter, all of it pales in comparison to the sheer dominance of dark energy. We know it's there, we see its effects, but its true nature remains elusive. This is the paradox at the heart of dark energy. Now let's rewind the cosmic clock a bit. Back to the early 20th century when Albert Einstein was developing his groundbreaking theory of general relativity. Einstein, in his brilliance, introduced a term in his equations called the cosmological constant. However, with Edwin Hubble's discovery of the expanding universe, Einstein famously called the cosmological constant his biggest blunder, discarding it from his equations. Little did he know, his blunder might hold the key to understanding the universe's greatest mystery. Now, before we dive deeper into the mysteries of dark energy, let's address a common point of confusion: dark energy versus dark matter. While both share the word dark, indicating our limited understanding, they are fundamentally different beasts in the cosmic zoo. Imagine dark matter as the invisible scaffolding of the universe. Dark energy, on the other hand, is a different beast altogether. Instead of clumping together like dark matter, it's uniformly distributed throughout space, acting as a sort of anti-gravity force, pushing everything apart. Picture this. You're on a train looking out the window and you notice that the trees, houses, everything in the distance seems to be moving away from you. That's the expanding universe. Now imagine that the train is not just moving at a constant speed, but it's accelerating, getting faster and faster. That's what dark energy is doing to our universe. Galaxies are not just drifting apart, they're racing away from each other at an ever-increasing rate. This acceleration, driven by dark energy, has profound implications for the fate of our universe. As dark energy continues its cosmic dominance, we see its effects not just in the accelerating expansion of the universe but also in the very fabric of space itself. Imagine the universe as a giant cosmic web, with galaxies strung along filaments and clusters forming at their intersections. Dark energy, with its repulsive force, is causing these voids to expand, pushing the filaments and clusters further apart. This void expansion is making the universe a lonelier place, with galaxies becoming increasingly isolated islands in a vast, expanding sea of emptiness. Now let's gaze into the cosmic crystal ball and ponder the ultimate fate of our universe. The prevailing theory, based on dark energy, paints a bleak picture. If dark energy continues to dominate, the universe will keep expanding, and that expansion will accelerate. Galaxies will eventually recede from view, their light stretched to long wavelengths, becoming invisible to our telescopes. The universe will become a cold, dark, desolate place. This scenario is known as the Big Freeze. So far, we've explored the profound effects of dark energy but haven't really tackled the biggest question of all. What is it? One idea emerges from the strange world of quantum mechanics. Quantum mechanics tells us that empty space is not really empty. It's a seething cauldron of virtual particles popping in and out of existence. These quantum fluctuations could hold the key to understanding dark energy. To unravel dark energy's mysteries, scientists use the equation of state. This equation W links dark energy's pressure and energy density. It predicts dark energy's future behavior. If W stays at -1, the universe ends in a big freeze. If W becomes more negative, we face the big rip. Hold on to your hats, folks, because things are about to get really weird. Some theories suggest that dark energy might be a sign of something truly mind-boggling: a multiverse. The multiverse hypothesis proposes that our universe is just one of many universes, each with its own set of physical laws and constants. Some physicists believe that dark energy could be a result of interactions between our universe and other universes in the multiverse. These interactions could manifest as a repulsive force, pushing our universe apart, much like what we observe with dark energy. To understand dark energy, we look back to the universe's infancy. The cosmic microwave background radiation, CMB, is a faint afterglow of the Big Bang. Discovered in 1964, it shows the universe 380,000 years after the Big Bang. Tiny fluctuations in temperature and polarization reveal early universe details. These fluctuations hint at dark energy's role in cosmic expansion. Cosmologists have developed a remarkable model describing the universe's evolution with astonishing accuracy. Known as the lambda CDM model, it incorporates dark energy, dark matter, and ordinary matter. Lambda refers to the cosmological constant, Einstein's so-called blunder, now a cornerstone of modern cosmology. CDM stands for cold dark matter, the invisible scaffolding holding galaxies and clusters together. We've already touched upon the possibility of a big freeze, a slow, chilling death of the universe. But what if dark energy has a more dramatic end in store for us? Enter the Big Rip hypothesis, a truly terrifying scenario that would spell a much more violent end to the cosmos. In this scenario, dark energy doesn't just continue to dominate the universe, it grows stronger over time. This growing dark energy density would have catastrophic consequences. First, it would tear apart galaxy clusters, sending galaxies hurtling away from each other at ever-increasing speeds. Then, the very fabric of space-time would begin to unravel. How do we know dark energy exists? How do we measure the unseen? Cosmologists use ingenious methods to measure dark energy's effects. Type Ia supernovae act as standard candles. Their predictable brightness helps measure distances. Observing their light reveals the universe's expansion rate. Neutrinos, those ghostly particles that zip through the cosmos at near light speed, might hold a key to understanding dark energy. These tiny particles interact very weakly with matter, making them incredibly difficult to detect, but they are incredibly abundant in the universe. While neutrinos were once thought to be massless, we now know that they have a tiny mass, albeit much smaller than any other known particle. This discovery has led some physicists to speculate that neutrinos could be playing a role in the cosmic acceleration. To unravel dark energy, scientists mapped the universe in detail. The Dark Energy Survey used a powerful camera in Chile to observe millions of galaxies. By studying these galaxies, DES measured dark energy's influence on the universe's expansion. The results provide valuable insights into dark energy. In the expanding universe, the Hubble constant plays a crucial role. It tells us how fast the universe is expanding at a given time. Measuring H0 accurately is crucial for understanding the universe's age, evolution, and the role of dark energy. However, there's a problem. Different methods of measuring H0 have yielded slightly different results, creating a discrepancy that has puzzled cosmologists for years. Remember those vast cosmic voids we discussed earlier, those regions of space with very few galaxies? Some of these voids are truly enormous, stretching for hundreds of millions of light years. These supervoids might hold clues about dark energy. Supervoids are not completely empty. They contain a small amount of matter, influenced by surrounding structures. Studying supervoids helps test dark energy models. Here's a rather perplexing question. Why is dark energy becoming dominant in the universe just as we humans have evolved to observe it? This question, known as the coincidence problem, has puzzled cosmologists for years. For most of cosmic history, dark energy played a negligible role in the universe's evolution. It was only relatively recently, on a cosmic timescale, that dark energy became the dominant force, driving the accelerated expansion we observe today. Is this just a random cosmic coincidence, or is there something more profound at play? The quest to understand dark energy is far from over. Scientists around the world are developing new technologies and planning ambitious experiments to probe the mysteries of this elusive force. One such mission is the Euclid Space Telescope, a European Space Agency mission scheduled for launch in 2023. Euclid will map the distribution of billions of galaxies over a third of the sky, providing precise measurements of the universe's expansion history and the role of dark energy. Another groundbreaking mission is the James Webb Space Telescope, the successor to the Hubble Space Telescope, which launched in December 2021. From its unexpected discovery to its potential role in the fate of the universe, dark energy has captivated the imaginations of scientists and the public alike. It's a stark reminder of how much we still don't know about the cosmos, a humbling reminder that we are constantly on the verge of new discoveries. As we continue to explore the universe, both near and far, we can be sure that dark energy will continue to challenge our assumptions and push the boundaries of our understanding. The universe is full of surprises, and dark energy is perhaps the biggest surprise of them all. Thank you for joining me on this cosmic journey.